this welcome to this class of microscale transport process. What we are discussing is various microfabrication techniques, in particular photolithography, and we have already discussed how to transfer a pattern using a mask and a mask aligner, and what is the use of photoresist, how this photoresist is coated on a silicon substrate. These points we have already discussed. We start this class with a discussion on wet etching. I must point out to you that the etching process that we discussed before, the etching involves dipping this I mean what I mentioned before is that etching involves dipping the substrate which has already been exposed and the polymer has already been solubilized. Okay. After this exposure and after this after putting this substrate into the developing solution, after all this process is done, okay, then you take this substrate and put into the etching solution, and etching involves reaction of silicon with the etching chemical, and by that way the product that forms goes to the solution and silicon is gradually etched, or a groove or a channel forms on the exposed part of the substrate. So, the etching can be of two types. One is referred as wet etching, where the silicon substrate after exposure and after development through after solubilizing the relevant resist part, this either it could be dipped in an etching solution which is a chemical solution, or it could be done by a process which goes by the name dry etching. So, etching can be of two types. One is wet etching, the other could be dry etching. Wet etching refers to dipping the substrate into a chemical and conducting a chemical attack, but that is through a liquid phase. So, that is what we refer here as wet etching. So, what we have here is wet etching involves subjecting parts of an object to chemical reactions and subsequent dissolution. Okay. So, keep in mind there is another process which goes by the name dry etching. Here we focus first in this slide the wet etching process. So, wet etching involves subjecting part of an object to chemical reactions and subsequent dissolution, so that a channel or a groove forms on the exposed part of silicon substrate. The other part, I mean depending on whether you are using positive resist or a negative resist, the other part which has not been solubilized with the resist, the other part where the polymer the photoresist has not been solubilized. So, the other parts are protected by a mask. This technique is used in 15th century to decorate armors. Wax is used as a mask there. Wax on parts identified for etching is cut out. So, that means on a metal plate wax is deposited, and depositing wax is no big deal. You understand what wax is. You have seen a candle and how wax melts. So, the wax is deposited on the metal plate, and the parts that are identified for etching, those are cut out. That means, in those places the wax is taken away. Then this metal plate is dipped into reactive bath for a period of time that ensures chemical etching or hollowed out pattern in places. So, the places where there is where the wax is taken out, in those places the etching is possible, chemical attack is possible, the chemical can access the metal plate and there a hollowed out pattern results in places places that are not covered by wax. Later wax is removed by heating this metal plate. Now, rate of etching follows Arrhenius expression. You must understand one fact here is that you have earlier dipped the substrate into a developing solution. If we go back to our previous discussion, in the typical protocol that we discussed, there near the end you can see we have mentioned that the system is dipped in developing solution for 3 minutes. This developing solution is primarily to dissolve the photoresist material. This is just a solubilization process. Okay. So, this does not involve Arrhenius type dependence on temperature. However, this etching is a reaction. Etching is a reaction of silicon with the dipping solution. So, this rate follows Arrhenius expression and is a strong function of temperature, unlike solubilization of resist. So, this is a very important point, you should note down that rate of etching is a strong function of temperature. So, when you calculate how long you should keep the substrate in the etching bath, that time you calculate, or when you consider the rate at which the etching will take place, that would be a strong function of temperature, unlike the solubilization of photoresist. Now, I must point out here, when it comes to wet etching, there are two types of etching possible. One is anisotropic etching and other is isotropic. Isotropic means it is identical in all directions. Anisotropic means it has some preference. It has some preference. It has a preferential etching in one particular direction. Now, here I would like to point out once again that this 1 planes of silicon are highly packed with atoms. Let me revise once again this, what this 1 plane is. Silicon crystal is made of, it is basically silicon follows a crystalline structure. It has the atoms are arranged in a particular manner. It is not like glass, which is amorphous and there is no particular arrangement. So, in silicon crystal the atoms are arranged in a particular manner, and that manner is that it is face centered cubic lattice, interpenetrating network of face centered cubic lattice. Face centered means you have a cubic lattice, that means a cube, that means atoms are placed on all corners of a cube. Face centered cubic lattice means over and above these atoms there are more atoms at the center of each face. Okay. So, other than the atoms in the corner, there are atoms at the center of the face. So, that is means you had these are the atoms. So, this is a cubic lattice and you have the atoms are in place. Okay. So, these are the atoms. Now, over and above these atoms you have atoms at the center of each face, there are atoms. Okay. Now, this is one face centered, this is a face centered cubic lattice structure. Now, I said interpenetrating network of face centered cubic lattice, that means you have one such cube, you place another cube on top and then move that cube by a distance, as I pointed out in the last class, 1/4, 1/4, 1/4 in x, y and z direction. So, in that case whatever structure that results, that would be considered this interpenetrating network of face centered cubic lattice structure, which is basically the crystalline structure of silicon. Okay. So, because of this structure you have 1 planes of silicon which are highly packed. This 1 this refers to the Miller index. Okay. In the last class we have discussed what Miller index is, and you have to look into this, how this 1 how these are defined. So, velocity of etching is slow along planes 1 and fast along 1 or 1 let me point out once again very quickly what this 1 plane is. As per the Miller indices, if I look at a cube, I find one plane, it is making intercept to the x, y and z axis. What is the value of that intercept? Okay. So, I will have intercept for the x axis, I will have another intercept for the y axis, another intercept for the z axis for each plane, and that intercept value, reciprocal of that intercept, these are these numbers that I have here. So, as far as this plane is concerned, this has an intercept on y at an unit distance away from the center. So, it is making an intercept at 1 as far as this y direction is concerned, but when it comes to the directions x and z, this plane does not intercept at all, or in other words it intercepts at infinity. So, when I look at 1 by 1, 1 by infinity and 1 by infinity, what I get is 0 1 0. So, that is what this plane refers to. Similarly, you can come up with a plane 1 1 1. So, that is what we are referring here, that in silicon crystal 1 1 1 planes are highly packed with atoms compared to 1 0 0 or 1 1 0, these other planes. And when it comes to etching, that means that silicon, this atom is reacting with the etching chemical. So, the etching process will be slower in 1 1 1 plane and etching process would be faster in other planes. So, there would be a preferential etching in one direction, that is what I am trying to get to. So, typical etching speed with KOH along 1 1 1 plane is 13 micrometer per hour. The etching speed is 60 times faster in other orientations. So, when you dip this substrate in the etching chemical, you will see the cutting of that crystal in one particular plane. Okay. It is not that it is uniformly being cut, that groove is formed, that depth it is not uniformly picked up, rather it would be cut in a particular direction. Can you tell me what would be a uniform etching? If it would have been an isotropic etching, how would it look? Suppose this part is protected by mask and only this portion is exposed. I mean, this portion etching can take place. Now, if it would have been an isotropic etching, for example, if you have glass does not have a crystalline structure, it is amorphous material. Okay. So, amorphous material means these are the chains are dangling here, I mean the atoms are random. So, you can you tell me how would be the shape of isotropic etching process if the etching would have been taking place uniformly in all directions, then it will not be this. This does not mean it is uniform in all direction. What it means, uniform should be this. Think of it, this is the point from which the etching is taking place and you should form a circle uniform in all directions. So, gradually this would be changing because the etching center would change. Okay. So, this is called isotropic etching. So, isotropic etching does not mean this is not isotropic etching either. Isotropic etching means this is isotropic etching. Okay. Now, this is what we have in silicon is an anisotropic etching, which I have already pointed out in this slide, that the etching speed is 60 times faster in other orientations and etching speed is in 1 1 1 plane is 13 micrometer per hour. So, this gives you some feel, 13 micrometer per hour. So, how long you have to keep this substrate into the immersed in the etching solution. So, this gives you an idea in that respect. Now, so therefore, you must agree that the etching happens preferentially along a crystallographic plane. We all agreed to that. The crystal will make the cutout forms appear spontaneously along the planes where the etching is lowest. So, there would be a cutout form which appears spontaneously along the planes where the etching is lowest. This form of etching makes possible cavities with facets which can be useful. What that means is that if somebody wants to see this is 1 1 1 plane, this is 1 1 1 plane, this plane is 1 1 1 plane, this plane is 1 1 1 plane, all right, and these makes an angle of 54 degree that we already pointed out, right. You remember in previous slide, the highest density planes form an angle of 54.74 degree to 100 plane. So, this is the angle of this is that angle. So, the groove that is being formed. So, this part is protected by mask, this part is protected by mask, and you are trying to create a channel on silicon substrate, and when you try to do that, what you end up with is a what I say here is this form of etching makes possible cavities with facets. So, you have an inclined face here, it is not a straight channel. So, this is what you are going to form when you go for a wet etching. Okay. Now, if this is something which you want, perfect, but there is a shortcoming to it, is that if you want to make a deep hole or a deep channel for some reason, if the channel that you want to make is a deep channel, in that case what you end up with is beyond some point. Suppose this, if you continue doing the etching, then it will end up here. Beyond this point you cannot etch anymore. So, suppose you want to make a deep channel, or if you want to make a through hole, okay, so you have to be careful. I mean, there is a limit there. I mean, up to certain point you can do, beyond certain depth probably you cannot. Okay. So, this point is there. However, in many situations you want the channel to be this way, and then this anisotropic etching is perfect. This type of etching is not possible in amorphous solids such as glass, that I already pointed out, because in glass what you will have is what we refer as isotropic etching. So, this isotropic etching is carried out equally in 3 spatial direction. Okay. So, it does not have any preference for any particular plane. So, this etching would be, if this is the area protected by mask, if this is the area protected by mask, you end up forming a channel which takes this kind of shape. This is a good example of isotropic etching. Example is etching of glass by hydrofluoric acid. Now, as I said, the etching can be of 2 types. One was the wet etching, that means you are conducting the etching by dipping the substrate in a liquid. Okay. Instead of that, there could be a process which goes by the name dry etching of silicon. Okay. Dry etching means it does not involve any liquid. It is done using energized ionic species. Attack of a substrate by an ionic species contained in gaseous or plasma phase, that is how dry etching is done. So, what you do here is you have, suppose this is the portion which is protected by mask. Okay. Now, what you are doing is you are exposed, this portion is exposed. So, it is bare silicon. It is actually having bare silicon is little difficult, because moment you keep it in oxygen, there would be a very thin layer of silicon dioxide forms on this layer, but this can be etched out fast, but there would be a very thin layer of SiO2. Now, that is probably not the point. What I make here is, what you have is, this is a bare silicon. Now, you have some ion, suppose this is a plus ion, and this ion is coming, this ion is bombarding the substrate. So, this ion is energized. How do you energize this ion? First of all, you apply a voltage, pretty high voltage, and then you apply vacuum as well. So, this medium is vacuum, you have certain selected gas which can be ionized, and then apply a voltage. Okay. These ions are energized, and these ions are pretty much they are ballistic. So, they bombard the surface of the substrate, and then there is a reflection also going on in this direction. Okay. So, automatically the plane that you cut, it has a layer like this, it forms, because when the reflection takes place, that reflection that will chip away the silicon material. So, automatically you develop an anisotropy, but mind it, this anisotropy is not caused by the crystalline structure. This anisotropy is caused by the system itself. You have chosen your system that way. I mean, these ions are bombarded and the path the ions are taking automatically, I mean, the ions are routed that way that it makes it forms an anisotropic, I mean it does anisotropic etching. So, attack of a substrate by an ionic species contained in gaseous or plasma phase, isotropy or anisotropy controlled by the etching process and not by crystalline structure. In wet etching, this anisotropy was controlled by the crystalline structure, but that is not the case for dry etching. Okay. And there are various forms of dry etching possible. First of all, the first one is physical etching, which it goes by other names as well, sputtering, ion beam etching, ion milling. So, these are all the same I mean they refers to the same etching process. The second method is chemical etching. Third one is physico-chemical etching. This also goes by the name reactive ion etching, in short form RIE, and the fourth one is physico-chemical etching with inhibitors, which goes by the name deep reactive ion etching, DRIE. Okay. Now, let us focus on first what the physical etching is. Physical etching, or which goes by the name sputtering, ion beam etching or ion milling, this involves a chamber. You apply vacuum here and you introduce some gas here. A common gas could be CF4, which can be ionized. Okay, CF4, CCl4 is carbon tetrachloride. CCl4 is used for certain form of chemical etching. This I mentioned about those 4 methods. The fourth one, DRIE, that use CCl4. Physical etching, it is done by CF4. This CF4 would be ionized. Now, here you have anode and cathode. Okay, so this is the anode, the upper one is the anode, and the lower one is the cathode, and here lies the substrate, this dark one. This dark one is the substrate. This is that silicon wafer, substrate, or I should write it as silicon wafer. So, this is the silicon wafer. This silicon wafer is placed on the cathode, okay, and you have this anode, and these ions are accelerated in an electric field. So, let me go back to let me look at the slide here. Ions are accelerated in an electric field 10 electron volt to 5000 electron volt generated between 2 electrodes. Okay. So, ions bombard the surface of a target. Ions bombard the surface of a target. So, ions are accelerated in an electric field. How the ions are formed? You introduce the gas, you created a vacuum, and by vacuum I mean it is a low pressure. So, low pressure helps in making the ions ballistic. Why do you have vacuum in the system, this chamber? Because this will help making the ions ballistic. You know what ballistic means? It will be easy for the I mean you will put more velocity, more momentum to the ions. So, low pressure of the order of millitorr. What is 1 torr? 1 torr involves 1 millimeter of mercury, the pressure equivalent to 1 millimeter of mercury. So, this is a very small pressure as such, and you are talking about 1 millitorr. So, you maintain a low pressure inside the chamber, and this low pressure helps in making the ions ballistic. So, you apply you put anode and cathode, put the silicon wafer on the cathode, introduce a gas which can be ionized. The typical example is CF4, you apply vacuum, so that the pressure inside the chamber is low, and you apply an electric field 10 electron volt to 5000 electron volt. Use of CF4 gas is common in ionization. The method is inherently anisotropic because of the pathway taken by the reflected ions. That is exactly what I pointed out just in the previous note, right, that you have, if this portion is masked and if you have this portion exposed, and if this is the ion that is coming from anode to cathode, because this silicon wafer is sitting on the cathode. So, plus ion is coming, is attracted towards the cathode. So, this is coming down, and then it is chipping away silicon, but chipping away, and when it is reflected, because of the pathway taken by the reflected ions, the method is inherently anisotropic. So, it does not depend on whether you have atoms packed in 1-1-1 plane or not. If you bring in some other material which does not follow a crystalline structure or is not packed in 1-1-1 plane, still you will see this anisotropy. That is what I want to point out. However, one negative aspect of this physical etching is selectivity about the portions of the substrate to be etched is poor. You need precisely, okay, this is the place where I want to etch, okay, and I need a precise groove formed at that place, and this physical etching process is less selective. Etching rate is 0.6 micrometer hour to 18 micrometer per hour for most materials. So, etching rate can be etching rate will vary, you must understand. Etching rate would be a function of how ballistic the ions are, what are the conditions prevailing. So, etching rate typically changes from 0.6 micrometer per hour to 18 micrometer per hour, and this etching rate defines how long you have to keep this silicon wafer in this chamber if you want to create a channel of certain depth. The next technique that I have here goes by the name chemical etching. Physical etching is where the ions are bombarded and ions are physically chipping away the silicon from the surface. In chemical etching, a chemical species which is a neutral species that migrates, chemical species migrate towards the target by diffusion. That means, if this was the example of physical etching, I have a similar situation. The silicon wafer, a portion of it is masked and the other portion is open for exposure. Now, I am exposing this to a chemical etching process. So, here we have a neutral species, it is not a charged ion. So, you have to mind one thing, that in chemical etching process you do not have any anode or cathode, you do not have any voltage applied, it is just a neutral species. Okay. What is the example of neutral species? I have given it in the second point, the reaction here. Chemical reaction occurs on the surface of the target. Here you have XCF2, okay. XCF2 is sublimated. Sublimated means it was in solid phase and it was brought from solid phase to gaseous phase inside the chamber. So, XCF2 in gaseous phase diffuses. So, this colored sphere that I have, this dark colored sphere, this is XCF2 in sublimated state. Sublimated means XCF2, a solid XCF2 was somewhere there nearby, and that XCF2 has been sublimated. That means, it has taken from solid phase to the gas phase, and one gas molecule XCF2 is floating around. It has a high diffusivity, you know, gas molecules can diffuse easily. So, it is getting in contact to the exposed surface, that is what we have. This XCF2 reacts with silicon in the silicon wafer. This XCF2 reacts with silicon to form Xc and SiF4, okay. And this Xc and SiF4 is volatile. So, SiF4 is volatile. What does that mean? The product is SiF4. So, Si is eaten away. Si is taken away, Si is silicon, silicon is taken away from the surface of the silicon wafer, and it is making a product which is not a solid. So, which is not sitting on the silicon wafer, rather it is volatile. So, it is going out. So, what you have here is a volatile product goes out, a volatile product goes out. So, here this is not a ballistic ion, I mean this process does not involve any ions which is bombarding the substrate. So, how is this XCF2, how it is coming in contact? Suppose I have etched some portion. Okay. Now, how is suppose I have formed a cavity already, but I am making it more deep. Okay. So, how is this XCF2 getting into that cavity for further etching? It is by diffusion only. A gas molecule diffuses. You know what a diffusion process is. I mean it is a very simple process, you do not need to energize or anything. Of course, molecule has its own energy, but it is like you have created a smell here, and somebody up that there in the corner of that room, he can smell it. It is that form of diffusion we are talking about. So, that diffusion should be uniform in all direction. These molecule will come in contact with silicon in all direction uniformly. So, what you expect is an isotropic etching happening, because it is governed the axis of this the movement of this XCF2 molecule to into the inside the groove is purely controlled by diffusion, and diffusion should be isotropic in all direction. It does not have any preference. It is not that this is bombarded and then it is reflecting, and it is the angle of inclination what matters. That is not that way. It is simply it is diffusing in a very gentle mode, and then it is going and accessing the silicon surface, having the reaction, and once the reaction is done, the product itself is volatile. So, product leaves the surface. So, this is what is chemical etching. So, both the products dissolve and diffuse back. Both the products, that means Xc and SiF4, both of them dissolve. They do not adsorb to the surface, they dissolve and diffuse back to the bulk. So, they go back to the bulk. So, you form an isotropic etching by this process. Chemical species not accelerated by application of voltage. So, if somebody asks you what is the difference between physical etching and a chemical etching, now you know that. All right. The other points that need to be noted here is volatile products here are not reflected. I pointed out this, it is not like ions which has an angle of inclination and a reflection. Movement is diffusive and not ballistic. So, mostly isotropic etching will result. Etching rate is micrometer per minute. However, the etched surface is rough, that is the people who are practicing it, that is what they said. Pressure is maintained at 0.1 torr to 1 torr. You may ask me why it should be, why the pressure is still low. If you have a low pressure, you can have probably a higher mean free path of molecules, and which you are trying to utilize here, because the molecule has to penetrate into the groove. So, probably something of that is happening there. It is pressure is maintained at 0.1 torr to 1 torr. Of course, the level of vacuum is not that much as it was in physical etching. Physicochemical dry etching. Now, at the very outset I pointed out that there are 4 types of dry etching possible. Here we are talking about dry etching and not wet etching, which we discussed before, putting the silicon wafer in a liquid and the etching takes place in the liquid phase, that was wet etching. This is dry etching, and under dry etching we have 4 categories: physical etching, which goes by other names as well, and probably the other names are more common. You might have heard of, okay, I have gone for iron, I mean this material has undergone iron milling, etc. So, we have discussed already the physical etching and chemical etching, the first 2 categories. When we come to the third category, physicochemical etching or physicochemical etching with inhibitor, you want to get the benefit of both worlds, physical etching process as well as the chemical etching process. So, that is what is referred as physicochemical etching, take the benefit of both processes. This physicochemical dry etching, that also goes by the name reactive ion etching, RIE. This is combined effect of physical and chemical etching. So, what that means? This means that you have, as before, you have a masked portion and you have a portion of the wafer which is exposed, which is open for exposure. Here you have a neutral species as it is in chemical etching, and also you have a ion as it is in physical etching, and both are doing the etching. Both are doing the etching, and incidentally, I mean, I can tell you how the shape would look like. I mean, it would be interesting, because one is isotropic and another is anisotropic. What I find is that the shape would be something like this. Shape would be something like this. So, this is what you have. You have both volatile products coming out. So, it will not be entirely depending on physical etching. So, the reflection of ion would be less, but still it is not isotropic. It is basically you are merging the two schemes. So, you can expect it would be halfway between the two, and that is probably what has happened here. So, that is how the shape would look like, and this shape, by the way, is not an isotropic one. This is what is isotropic etching. This is still anisotropic, but it is not forming a facet, forming a slanted surface. So, here this reactive ion etching is commonly used in micro fabrication. It is a more common method, this reactive ion etching, than other techniques. It is a combined effect of physical and chemical etching. Here the target is placed on the cathode. We have already discussed how the physical etching was taking place. You remember that you have an anode, you have a cathode, and you have the silicon wafer sitting on the cathode. So, here also the same thing is happening. You have, because you will have this gas, you will have target placed on the cathode. Cold plasma breaks down CF4 to CF3 plus F minus and makes the ion ballistic at low pressure. Okay. So, this is having an etch rate 10 times that of physical etching. So, this etching process here, the etching rate is 10 times that of physical etching, and good in etching silicon dioxide. Wet etching of silicon dioxide takes time from the surface of silicon wafer. So, what essentially the last 2 points, what they mean is that physicochemical dry etching is good to etch silicon dioxide. Silicon dioxide, as I said, silicon dioxide will form automatically. If you leave a bare silicon in atmosphere, the oxygen is there, that oxygen will react and it will form a nanometer scale layer of silicon dioxide. It will form automatically, okay, and that has to be etched. So, any etching you start, the moment you start the etching process, you have to first etch silicon dioxide and then etch silicon. And etching silicon dioxide is not that it's more difficult than etching silicon. Okay. And in some cases, you intentionally give us a silicon dioxide cover on silicon surface. If you heat silicon wafer to say 600-700 degrees centigrade in oxygen in air, automatically you will form a silicon dioxide layer which is much thicker, and that breaking that silicon dioxide layer would be difficult. That breaking that silicon dioxide layer simply by wet etching is difficult. Typically, this dry etching process is good to chip away that silicon dioxide layer. More importantly, this physicochemical dry etching, since it is 10 times faster than physical etching, this method is further, I mean, it is preferred to etch silicon dioxide layer. So, if you have a question in your mind, why do I etch silicon dioxide? Because I was working with silicon wafer, you said it is a monocrystal and you have all kinds of things, face centered cubic lattice, etc. Why am I getting into silicon dioxide? Because this is because silicon dioxide automatically forms if you leave it in atmosphere, and at times you can have silicon dioxide as a mask intentionally made on silicon wafer, and you have to etch that silicon dioxide first. You have to remove that layer, then only you can get in contact with the bare silicon. So, etching that layer is this method of physicochemical dry etching is good. The fourth method, as I said, you are taking benefit of both physical etching and chemical etching. On top of that, you have another addition to it, which is physicochemical etching with inhibitor. Inhibitor is a new item here, inhibitor. This method also goes by the name deep reactive ion etching, DRIE, and this is very common. I mean, if somebody is making a through hole in a silicon wafer, that means you have a silicon wafer which has a thickness of 500 micrometer and you want to make a through hole, and that hole diameter has to be very small. So, you are creating a hole which has a very high aspect ratio. That means, what I mean by aspect ratio, I have a silicon wafer, this is the wafer, this is the wafer, and I want to make a through hole like this through the wafer. This will not be very easy. If you are going by weight etching, it would be anyway slanted. So, beyond a distance you cannot etch. If you are doing a physical etching, you will end up with some kind of anisotropy because of this bombardment and reflection of ions. So, at one point you will it is not possible. This thickness of a silicon wafer, I said, is 500 micron, and if this diameter of the hole is less, say we are talking about say 10 micron or 20 micron. So, you can think of the aspect ratio of this and how will you etch this. So, that is an issue here, and this deep reactive ion etching is very popular technique for doing this job. The way it works here is that it is basically a physicochemical etching. However, the reaction products, in case of a chemical etching, I said it is the reaction product, the product that is formed is volatile. So, it dissolves from the surface and diffuses back to the bulk, but here the product that is formed, I mean, so you are tailoring this process in such a way, so that the product that is formed, it is non-volatile, the reaction product is non-volatile. You can achieve this by you choosing the gas carbon tetrachloride instead of CF4, you need to use Cl4. So, non-volatile component, which we are referring here as inhibitor, is deposited on the neighboring vertical surface. What does that mean? You have this portion masked and you have this portion as exposed as before, the silicon substrate here, and then you are forming you have introduced one, it is basically physicochemical etching. So, you have a neutral species and you have a ion, and both are doing the job. Now, the product that is formed, it is neither the chemical, see the ion whichever is reflected, it will go out. Okay. However, this chemical entity that is there, the product that is formed, that is not diffusing out, rather that is a non-volatile product. So, what will happen is that will stick to the surface. So, what you end up with is you will have a coating forming, this inhibitor will form, this will form a coating, this is the layer. A coating would be formed in the vertical wall, a coating will be formed. This coating is made of product of this chemical etching process. In a chemical etching process, the product was volatile, so it can diffuse back to the surface. Here the product is not volatile, so it will be deposited next door. So, next door is basically the vertical surface, because this product is trying to rise up, but since it is not volatile, it has to stay there itself. So, what you end up with is a polymerized protective film formed on the vertical surfaces. So, it is your choice of the chemical that you have which is making this making this protective film. So, I repeat once again, physicochemical etching with non-volatile reaction products, the gas here is CCl4, non-volatile components. Non-volatile component, which is referred as inhibitor, is deposited on the neighboring vertical surface. A polymerized protective film is formed on the vertical surface. Now, this film protects the vertical surface from the reflected products. So, ions are reflected back, and on the way it creates the anisotropy. That is how physical etching was happening. Here this protective cover will ensure that no more chipping takes place from the vertical surface. So, the film protects the vertical surface from the reflected products arising from ballistic ions, because you had ballistic ions as well as chemical species both present there. So, therefore, very deep structure of the order of 500 micrometer with aspect ratio of 30:1. 30:1 means 1 is the diameter of that hole and 30 is the depth of that hole. That kind of aspect ratio is achievable. So, this DRIE method is truly very popular method if somebody wants to make a through hole in a silicon wafer. In many occasions that is required, and through hole with high aspect ratio. So, 500 micrometer means okay, it is palpable, and 500 micrometer I can see on a ruler, but as I said 10 micrometer, the aspect ratio, creating that aspect ratio, this method is very popular. And making a through hole of high aspect ratio is difficult from wet etching due to anisotropy. This you already have appreciated. So, we have already discussed how to do the etching. We have so you have to we have a process which goes by the name spin coating, which was used to coat the substrate by photoresist material. Then we have a mask aligner to set a mask on top of that. Then we have a light source, and we illuminate. We change. We have chosen the photoresist material which has certain photo solubility properties, and by that method we have created an exposed part and an unexposed part, and then we have, after we have done that, we have gone for the etching process. Etching can be of two types, it could be wet etching or it could be dry etching, and this wet etching and dry etching processes I have already discussed. I mean, by now you should get an overview of how these systems work. Now, once you have created the channel, so what you have done, you have taken a silicon wafer 500 micrometer thick, other dimension is 4 inches, and you have taken that wafer and you have created a channel. If somebody wants to make a T joint, he can do that. So, you have engraved a channel on that substrate. That part is done. Next, what needs to be done? If you are creating a microfluidic or micro scale structure, on that channel there needs to be a deposition of other material. Okay. And once the deposition is done, probably you have to put a lid on top of this. So, you have to take another wafer and put it as a lid, okay, and then bond it, and then you have to make some external ports. You have to put some external ports, so that these bonded the two layers, that sandwich that you form, then that has some connection with the external world. So, that when you are putting the fluid, putting the sample, you can put it. So, you need some connection, some inlet outlet ports in that microstructure device, and you are done. So, what you have done, you have taken a silicon wafer, you have created a channel, created one channel, multiple channels, whatever you want. Okay. Now, within that channel you will have catalysis, within that channel you have reaction happening, within that channel you will have electrodes, within that channel you will have separation. So, everything will happen there inside the channel. Channel can be will have a circular geometry. That depends on how you designed your mask and how you transferred the pattern. Okay. Once you have done the channel, then the other thing that you need to do is you may have to deposit some other material inside the channel. That is a possibility, and then at the end of it you have to take another wafer and put it on top and then bond it, so that this whole system becomes watertight. You put a sample and the sample should not leak from the side. So, you have to make a truly strong watertight structure, and then you make inlet outlet ports. So, that the structure can interact with the external world, and then you are ready. That is what your microstructure device is. So, once we are done with this, so we can say that okay, this is the microstructure device I have, and it will start, you can start the play with that instrument. So, we have already talked about how to make the channel. Now, we are getting into this deposition on silicon and glass. Deposition is required to form electrode, catalyst, thermal or electrical insulation, adsorbent optical elements on the wall of the channel. So, for these reasons you need to deposit the material inside the channel. So, deposition could be you are probably forming an electrode at one end of the channel, not over the entire channel, only in one portion. After the sample mixes with the reagent and they flow, then they undergo passive mixing, then they undergo some operation, and then it has to be you may be looking into this electrical field flow fractionation by where you are basically putting them in banded in layers using 2 electrodes. So, electrode has to be placed on the channel, one anode, one cathode should be there on the wall of the channel. So, how will you deposit this material on the channel? There are 2 ways it is possible. One goes by the name physical vapor deposition and the other goes by the name chemical vapor deposition. Here we are talking about deposition. I mean earlier we have talked about physical etching and chemical etching. There our objective is to take away the silicon from the substrate, so that you can form a groove. Here the idea is to deposit another material on that groove, okay, and that deposition is possible by physical method or chemical method. In physical vapor deposition, certain species from the holding gas is adsorbed on the surface of the target. Certain species from the holding gas is adsorbed on the surface of the target. 2 types are thermal evaporation and sputtering. There are 2 types of physical vapor deposition possible. One goes by the name thermal evaporation and the other goes by the name sputtering. I will discuss this in the next class, what this thermal evaporation and sputtering, what are these. The other deposition method is chemical vapor deposition. This is the short form is CVD, and it is again a very popular technique. Here certain species from the holding gas reacts with the target, forming compounds that are chemically bonded to the target. So, you have a chemical reaction happening, you have chemical vapor deposition, and when it is done just by a physical adsorption method, it would be physical vapor deposition. You can of course, there is a deposit, you can always go for an electrolytic method for deposition. You have already studied what this method is, how to make a electrolytic deposition. You put it in an electrolytic bath from a liquid form, you can make a deposition. Of course, you may say that it is you can even do a precipitation. You can have that material precipitated on the surface. However, one thing I would like to tell you at the very outset, that why people are going through this route, why they are going for deposition from vapor phase. I mean deposition on silicon and glass, but nobody is talking about deposition in the form of precipitation or things like that. Here you are talking about deposition from the vapor phase. The advantage here is that when you are in vapor phase, the diffusivity of the molecules are or the molecules can access the substrate, can access the surface much easily. Okay. So, if a crystalline structure forms, that crystalline structure would be it would be more homogeneous, but if it is a deposition from the liquid phase, then there would be mass transfer limitations coming into play. You know that diffusivity in a liquid phase and diffusivity in the gas phase, they are different, they are orders of magnitude different. So, there could be mass transfer limitations. Just you think about it, I mean what could be this how this problem would be. Of course, this chemical in the next class I will discuss what is physical vapor deposition and chemical vapor deposition are, but these deposition from the liquid phase, from a liquid bath, is also very popular by the way. However, these vapor phase depositions are little costly, and it is they have definitely some advantage to offset the cost. That is why people are, that is why still these methods are also popular, that you have to bear in mind. Okay, so in the next class I will discuss this physical vapor deposition and chemical vapor deposition. Thank you.